I'm Allison Campbell, and I'm the Acting Associate Laboratory Director for the Earth and Biological Sciences Directorate, and I'm here with John Shilling, who's in the Atmospheric Sciences Global Change Division. So John, tell me a little bit about yourself and how long you've been here.
Sure, I came here in September of 2008, so just a little over 7 years now. Okay. I came here out of a postdoc from Harvard to really kind of build something special here.
Yeah, so what's your area of expertise?
Aerosol chemistry,
so
specifically organic aerosol chemistry.
So these are things in the atmosphere that are flying around and undergoing chemistry?
Yeah, so what we study is the processes by which gases transform to particles in the atmosphere. Most of the particulate mass comes from this process where trees or other VOCs, organic molecules, are emitted, and they oxidize and they turn into particles, and that's where most of the particle mass comes from.
So for a lay person, a tree emits a molecule, and that molecule goes into the atmosphere and is oxidized because there's oxygen around, and then becomes a particle.
That's right, yeah.
And then that particle further reacts, and you're studying the formation and the life cycle of
That's right, the whole entire life cycle, from the formation to the eventual removal through cloud processes.
Okay, so how do you do that?
Yeah, so we're standing in front of what we call an environmental chamber, and it runs a little bit differently than a lot of other environmental chambers run. But the big idea is that we try to simulate those processes of gases being emitted, being oxidized, and then turning into particles in a really controlled way here in the lab.
Okay.
So
do you instrument them? I mean, I think I see some sort of instrument here.
That's right. So the other part of my job is actually to go out on Battelle's G1 and fly these same instruments around and see what actually is there in the real world in the atmosphere. Okay. So what we do is we take that data and we generate some kind of hypotheses about where the particles are coming from, where they're not coming from, what kind of processes are important in their life cycle. And then we come back with those same instruments here to the lab, and we try to simulate those processes here under very controlled conditions.
So you talked about the aerosols being formed in the atmosphere. So why is that important to folks on the street? What do they need to know about that?
Sure. Well, there's really two ways that they're very important. They can impact the light that's coming from the sun. So when it's really dusty out or there's really bad wildfires, you can obviously see that there's not a lot of light reaching the sun. Well, if that light is not light from the sun reaching the surface, if that light's not reaching the surface, it's getting lost somewhere, and that has an effect on the climate. Right. But probably the more relatable way that this is important is that clouds only exist because these particles exist in the atmosphere. If there were no particles, there'd be no clouds. Every cloud drop has at its center one of these particles. So it's extremely important for a wide range of things, ranging from precipitation to drought to climate, to understand how these particles influence clouds.
Yeah, so now you're talking my language, because I studied crystal growth.
That's right, and these particles may also...
They're nuclei.
These particles are nuclei, and they can also get up into the upper areas of the atmosphere where ice crystals form, and they have a effect there too.
Right. So they seed the clouds. Clouds form, and then we all know that clouds interact with weather and climate and all those sorts of things.
That's right, and we try to understand the relationship between particle chemistry and the ability of the particles to nucleate these cloud droplets.
Well, thanks.
Okay, great. Thanks.
All right. Appreciate it.
Thank you.